The ERC20 Token Standard defines the interface that a token contract must implement. This is the interface defined by ERC20. Let's start implementing this interface step by step. First, we define the essential fields owner, total supply, balances, and the events transfer and approval. This is pretty straightforward. In the constructor, we set the total supply of tokens, the owner, and the smart contract. To start, we establish all the coins belong to the owner. This smart contract will use the total supply defined during the contract creation, and there's no way to create additional tokens after deployment. The requirement for the function total supply can be solved by using the public keyword during the definition of the total supply field. The public keyword automatically exposes a getter function, also called total supply, that can be called publicly. For keeping track of balances, we need a mapping. This will map addresses to numbers, the user accounts to their balances. The transfer function accepts two parameters, the recipient and the amount to send. The amount to be sent will be deducted from the balance of the function caller, message.sender. Before we deduct the value from the caller's balance, first we must confirm that they have enough funds to transfer by using the assert statement. If the assertion is satisfied, we deduct the funds from the sender. Then we try adding the funds to the receiver and a new variable result that has the same type, uint256, as the balances we just mapped to these addresses. We must assert that the balance of the receiver has increased after the transfer. This is a check against overflow errors. In the end, we generate a transfer event before the function returns. Finally, we have the balance of getter function, which returns the balance for a given address. The implementation so far can perform the basic functionalities of tokens, hold balances, and transfer tokens. There is nothing we haven't seen before. However, there are a few more functions that provide more advanced functionalities, so we'll look at those next. The ERC20 introduces an allowance mechanism. This set of functions allows the account owner to provide specific allowances to many different accounts. To accomplish this in our smart contract, we must map the provider's address to a set of different accounts, each with specific allowance value. Essentially, we need to keep a balance book for each separate account. For this, we will use a mapping of addresses to nested mappings of allowances. Every nested allowance mapping will be address uint256. We also need a getter function for this mapping called allowance. To give someone an allowance, we use the approve function. We only need to add a record in the allowed mapping. However, if we leave it like this, there is a hidden bug in the code where the spender can spend more money than he has been allowed. Imagine the following scenario. Alice makes an allowance to Bob to spend N coins. Then she changes her mind and wants to decrease the allowance from N to M. If Bob has already spent the N coins before Alice makes the change to M coins, Bob will be able to spend a total of N plus M coins. There is no easy way for Alice to make sure this didn't happen without checking all transactions on the blockchain. That is why we will add a require statement before the first line in the function. This requires the allowance value to be 0 or the previous allowance for the spender's account to be 0. Given our previous scenario, Alice will have to set the allowance from N to 0. Check how much money Bob has already spent, then create a new allowance of M tokens or no allowance at all. Next up is the transfer form function. This one will be used by spenders to spend coins from their allowances. It accepts three parameters, the address from source and to target, and value. First, we get the remaining allowance and make sure that it's greater than the value to be transferred. Then we subtract this value from the allowance and add it to the recipient's balance. Last, we need to subtract the value from the original owner's total balance. During the execution of the function, if any of the assert statements fail, all previously executed commands will be rolled back and the entire transaction will fail. Now that our contract is finished, let's deploy it with Truffle. First, we put our code in the DailyToken.sol file in the contracts directory. Then we alter the migration file called toDeployContracts.js located in the migrations folder. We import our smart contract just like the other contracts. But in the deploy function, we need to pass two additional arguments for our smart contract. These extra parameters will be passed to the constructor of our contract, In our case, we need the total supply and the address of the contract's owner. I use an address from the 10 default accounts that appear in the terminal after running Truffle develop. Now, on to deployment. Let's start fresh by deleting the build directory. Compile our contracts, deploy. In a separate terminal, run Truffle develop. In the first terminal, run Truffle migrate. Let's interact with our daily token using the console. Check the output of the Truffle migrate command. You will see the address where DailyToken is deployed. Mine is... I can see that instance of the DailyToken with... To be sure, let's check the owner of this instance. In my case, this matches the argument I added to the constructor in the migration file. Check the total supply. Finally, let's check the owner's balance. Now name two accounts, parent and child. We'll use the owner's account as parent since that's where all the coins are. Let's create an allowance to the child account of 100 coins. While creating the allowance, an event called approval will be generated. We can listen for that event in another terminal window. Open another terminal into the same folder, then run Truffle develop. This second terminal will connect to the same network as localhost 9545. Get a handle for the deployed smart contract. The event accepts a filter argument. In this case, we want all events from first to last block. Set up the actual listener. When you run this event watcher, it will return any previous events as well, because we specifically said listen for all events from block 0 to the latest one. Now create the allowance call in the first terminal. Notice in the listener terminal the generated approve event. Today, we deployed our custom smart contract and interacted with all its functions via terminal. Also, we listened to events from another blockchain node. This is very much in line with the async architecture of technologies like Node.js and gives us an idea on how real-world applications can be built.